When running an insulated grounding conductor inside flexible metal conduit, often referred to as flex, for a three-phase convection oven, the necessity of grounding bushings hinges on the type of enclosure openings you're dealing with. Grounding bushings, specifically designed to bond the metal conduit to the equipment grounding system, become critical when dealing with concentric or eccentric knockouts. These knockouts, by their very design, introduce impedance to the ground fault current path. Impedance hinders the flow of fault current back to the source, which can delay the operation of overcurrent protective devices like circuit breakers or fuses. This delay can increase the risk of electrical shock and fire. A grounding bushing helps reduce the impedance. Concentric knockouts feature multiple rings of metal that can be removed to accommodate different conduit sizes. Eccentric knockouts are similar but have an offset center. When these knockouts are used, they leave behind a non-continuous surface with limited contact between the conduit and the enclosure. This limited contact creates the impedance. The grounding bushing, installed at the point where the conduit enters the enclosure, provides a secure, low impedance path for fault currents to flow. It ensures that the conduit is effectively bonded to the enclosure, creating a reliable grounding connection. However, the situation changes when you are not using concentric or eccentric knockouts. If you are utilizing a purpose-made knockout or opening designed specifically for the conduit size, and if that connection provides a tight, mechanically sound, and electrically conductive bond, then grounding bushings may not be required. The key here is the integrity of the connection. If the conduit is making solid, continuous contact with the enclosure, offering a low impedance path for fault currents, the additional bonding provided by a grounding bushing becomes redundant. In such cases, the grounding conductor running inside the flex provides the primary grounding path. The insulated grounding conductor plays a crucial role in the equipment grounding system. Its purpose is to carry fault current back to the source in the event of a ground fault. This fault current triggers the overcurrent protective device, disconnecting the circuit and preventing electrical hazards. The size of the grounding conductor is determined by the size of the overcurrent protective device protecting the circuit as specified in the National Electrical Code, or NEC. The NEC outlines the requirements for equipment grounding conductors in Article 250. In general, the grounding conductor must be sized large enough to safely carry the maximum available fault current without overheating or causing a voltage drop that could impede the operation of the overcurrent device. To ensure compliance with the NEC and local electrical codes, it's essential to carefully examine the specifics of the installation. This includes verifying the type of enclosure openings used, the tightness and conductivity of the conduit connection, and the proper sizing of the grounding conductor. Consulting with a qualified electrician or electrical inspector is always recommended, especially when dealing with complex electrical installations or when unsure about the applicable code requirements. They can assess the specific circumstances of the installation and provide expert guidance on grounding and bonding practices. Furthermore, it's important to distinguish between equipment grounding and bonding. Equipment grounding, as described above, involves creating a low impedance path for fault current to flow back to the source. Bonding, on the other hand, involves connecting metallic parts together to create an electrically conductive path that ensures electrical continuity and minimizes voltage differences. Bonding is crucial for preventing electrical shock hazards, especially in areas where people may come into contact with metallic surfaces. In the context of the three-phase convection oven, bonding may involve connecting the metal frame of the oven to the equipment grounding system. This ensures that any fault current that may flow to the frame of the oven is safely conducted back to the source, tripping the overcurrent protective device. The NEC provides detailed requirements for bonding in Article 250. Part 6 specifically addressing bonding of equipment and enclosures. Proper bonding techniques include using bonding jumpers, bonding screws, and other listed bonding devices. These devices ensure a secure and reliable electrical connection between the metallic parts. The NEC also addresses the use of flexible metal conduit in Article 348. It specifies the conditions under which flexible metal conduit can be used for grounding purposes. In general, flexible metal conduit can be used as an equipment grounding conductor if it meets certain requirements, including being listed and having a ground fault current path that meets the requirements of the code. However, it's often preferable to run a separate insulated grounding conductor inside the flexible metal conduit, especially in situations where the integrity of the conduit as a grounding path is questionable. This provides a redundant grounding path and enhances the overall safety of the electrical system. When installing the insulated grounding conductor inside the flex, ensure that it is properly connected to the equipment grounding terminals at both ends. Use appropriate connectors and ensure that the connections are tight and secure. Avoid creating any sharp bends or kinks in the grounding conductor, as this can increase impedance and reduce its effectiveness. Also, be mindful of the potential for corrosion, especially in damp or corrosive environments. Use corrosion-resistant connectors and consider applying a protective coating to the grounding conductor to prevent corrosion. Regularly inspect the grounding system to ensure that all connections are tight and free of corrosion. Address any issues promptly to maintain the integrity of the grounding system. Remember, a properly installed and maintained grounding system is essential for electrical safety. It protects people from electrical shock, prevents fires, and ensures the reliable operation of electrical equipment. The NEC provides the minimum requirements for grounding and bonding. Adhering to these requirements is crucial for compliance with electrical codes and for ensuring the safety of the electrical system. In summary, when running an insulated grounding conductor inside flex for a three-phase convection oven, grounding bushings are typically not required if you are not using concentric or eccentric knockouts and the conduit connection provides a tight, mechanically sound, and electrically conductive bond. However, it's always best to consult with a qualified electrician or electrical inspector to ensure compliance with the NEC and local electrical codes. They can assess the specific circumstances of the installation and provide expert guidance on grounding and bonding practices. Also keep in mind the equipment grounding and bonding requirements, and that flexible metal conduit is used in accordance with Article 348. The grounding conductor must be properly connected at both ends and free of corrosion. Regular inspections are needed to ensure that the connections remain tight and secure. By following these guidelines, you can ensure that the electrical system is properly grounded and safe. Let's delve deeper into the specifics of grounding and bonding as it applies to your three-phase convection oven installation. The NEC, specifically Article 250, provides comprehensive guidelines for grounding and bonding electrical systems and equipment. Understanding these guidelines is crucial for ensuring electrical safety and code compliance. As mentioned earlier, the equipment grounding conductor, often referred to as the EGC, plays a vital role in providing a low impedance path for fault current to return to the source. This path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. The size of the EGC is determined by the rating of the overcurrent protective device protecting the circuit. Table 250.122 in the NEC provides the minimum size requirements for EGC based on the size of the overcurrent protective device. For instance, if the three-phase convection oven is protected by a 30-amp circuit breaker, the minimum size of the EGC would typically be 10 American wire gauge or AUG copper wire. However, it's essential to consult the specific requirements of Table 250.122 to ensure that the EGC is properly sized. In addition to sizing the EGC correctly, it's equally important to ensure that the connections are made properly. The EGC must be connected to the equipment grounding terminals at both the source and the load ends of the circuit. These terminals are typically identified by a green color or a grounding symbol. When making connections, use appropriate connectors that are listed for grounding purposes. These connectors are designed to provide a secure and reliable electrical connection. Avoid using wire nuts or other general-purpose connectors for grounding connections, as they may not provide adequate conductivity or mechanical strength. In situations where multiple circuits share a common raceway, such as flexible metal conduit, it's permissible to install a single EGC to serve all of the circuits. However, the EGC must be sized based on the largest overcurrent protective device protecting any of the circuits in the raceway. This ensures that the EGC is capable of safely carrying the maximum available fault current. Now let's turn our attention to the bonding requirements for the three-phase convection oven. As mentioned earlier, bonding involves connecting metallic parts together to create an electrically conductive path that minimizes voltage differences. This is crucial for preventing electrical shock hazards, especially in areas where people may come into contact with metallic surfaces. The NEC requires that all non-current carrying metallic parts of electrical equipment be bonded together. This includes the metal frame of the convection oven, the metal conduit, and any other metallic enclosures or components that may become energized in the event of a fault. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metallic parts together. Bonding jumpers must be sized according to the requirements of the NEC and must be securely connected to the metallic parts using appropriate connectors. In addition to bonding the metallic parts of the equipment, it's also important to bond the metal conduit to the equipment grounding system. This can be accomplished by using grounding bushings, as discussed earlier, or by using other listed bonding devices. The purpose of bonding the conduit is to provide a low impedance path for fault current to flow back to the source, thereby ensuring the rapid operation of overcurrent protective devices. In some cases, the NEC may permit the use of the metal conduit itself as the equipment grounding conductor. However, this is only permissible if the conduit meets certain requirements, including being listed and having a ground fault current path that meets the requirements of the code. It's often preferable to run a separate insulated grounding conductor inside the conduit, as this provides a redundant grounding path and enhances the overall safety of the electrical system. The use of flexible metal conduit for grounding purposes is addressed in Article 348 of the NEC. This article specifies the conditions under which flexible metal conduit can be used as an equipment grounding conductor. In general, flexible metal conduit can be used as an equipment grounding conductor if it meets certain requirements, including being listed and having a ground fault current path that meets the requirements of the code. However, it's important to note that the length of flexible metal conduit used for grounding purposes is typically limited to a maximum of 6 feet. This is to ensure that the impedance of the conduit remains low enough to provide an effective grounding path. When installing flexible metal conduit, ensure that it is properly supported and that the connections are tight and secure. Avoid creating any sharp bends or kinks in the conduit, as this can increase impedance and reduce its effectiveness. Also, be mindful of the potential for corrosion, especially in damp or corrosive environments. Use corrosion-resistant connectors and consider applying a protective coating to the conduit to prevent corrosion. Regularly inspect the grounding and bonding system to ensure that all connections are tight and free of corrosion. Address any issues promptly to maintain the integrity of the system. Remember, a properly installed and maintained grounding and bonding system is essential for electrical safety. It protects people from electrical shock, prevents fires, and ensures the reliable operation of electrical equipment. Always consult with a qualified electrician or electrical inspector to ensure compliance with the NEC and local electrical codes.